So the gas package. For the first 4 bullet points are junior high, and you should know it. And why are gases compressible? Because
There's space between them.
wow! And I bet you're such good students. You've even written that down already. Really good. Done. Okay, so gases are compressible because they have spaces between them, so I can squish them together. So those 4 things on the first bit of the package are just junior high. You should know them, and I expect, just like I expect you to know the metal properties, I expect you to know these as underlining. So there are 3 things that can affect a gas: pressure, temperature, and volume. And I've talked about a balloon. And if I decrease the volume inside that balloon, you can understand that the pressure will change. And if I warm that balloon up, the particles are no longer just moving like this. Oh, something else to add to your junior high list is that they move in straight lines. I was just doing this. Gases move in
Junior class change.
straight lines. So they're like pool table balls, right? Anybody play pool?
Yep.
Snooker, billiards? You played it before? Okay. So you hit a ball, it travels in a straight line until when?
Hits.
Right, it hits something else. And then it angles, depending on the angle that it hit, and depending on the motion of that, that's exactly like gas particles. Okay, so gas particles move in a straight line until they hit each other, then they perhaps change their course, or they hit the sides of the container and then they change their course. Okay, so 3 things that can affect a gas is the temperature, how fast they're moving, that'll affect the pressure or expand the volume of the container if it's expandable. So all 3 of these things are related. Okay, so the gas unit starts by looking at these 3 things and how they interact with each other. And there are 3 scientists that we look at, well actually 4, but we'll get there. 3 scientists or 3 experiments that were done to look at how they're related. So not just, okay, it just makes sense. If I push a balloon down, I increase the volume, or decrease the volume and increase the pressure. That makes sense. But what if I squish it in half? Does it change the pressure by doubling it? Half, right? Half, double? Or maybe 4 times, or maybe 6 times? And what about a third? Does it 3 times or 9? Is there a relationship to the numbers between the volume and the pressure, the change? Okay? So the scientists went and did these experiments to look at these. But if I'm looking at volume and pressure, what must I do to my temperature? Keep it constant, or make it my controlled variable in my experiment. I need to control the temperature, because if it changes, that will have an effect on the pressure and volume. So if I change the pressure and the temperature, gosh, how do I know which affected what? So the first law we're going to look at is Boyle's law, and he kept the temperature as the control variable, and he looked at how pressure and volume are related to each other. Does that make sense? And so the graph that you're about to do looks at that relationship as if you were Boyle, as if you designed an experiment, and you are going to do some graphs and see if you can find a relationship in the numbers between them. Makes sense? But before I get there, I need to talk a little bit more about pressure. Okay? There are 3 kinds of units for pressure. So this is the middle of the package of the first page. There are 3 kinds of units. The first is kilopascals. Have you heard of kilopascals before? Okay, you might see on a tire or on a ball to fill up to a certain amount of kilopascals. It's obviously a metric unit, or an SI unit, System International, with the kilo, like a kilogram, and a kilo mole, and a kilo, what else? Meter. This is a kilopascal. Okay, so that's the metric. Then you've got the old-fashioned imperial unit of atmospheres. And that's based on, the atmospheres is based on sea level pressure. Okay, so 1 atmosphere of sea level. Oh, that makes sense. And then you can kind of go, oh, half the pressure would then be 0.5 of the sea, right? Kilopascals, and they had to change to be metric. And then this other old-fashioned unit called millimeters of mercury. You need to know all 3. You know how, like, I never talk about miles, right? Because it's just not scientific. So I don't talk about miles, but I will talk about atmospheres and kilopascals. So I talk about kilometers, I don't really talk about anything else. Here, for pressure, I talk about all three things. Mostly because they're still used a lot, everywhere. Okay, so you still might have atmospheres written on something, how many atmospheres you can fill it up to. Okay? And millimeters of mercury is often used in weather systems. Like when you're talking about the weather, you talk about how many millimeters of mercury. It's just a really old system because before you had instruments that were, you know, little computers basically to measure it for you, the weathermen that did the climate change. Has anybody been to Sulphur Mountain? Yeah, and you take that gondola up or you hike up. Have you never done this in Banff? You need to do it. You need to do it. It's amazing and it's super easy if you take the gondola.
Yeah.
And it's not so hard. The walk is not, the hike is medium level. You see people doing it in high heels that are true tourists. But, so you can hike down instead if you want. So you take the gondola up, and up there's like a cafe and a gift shop. And then there's like a boardwalk. When I was growing up, it wasn't a boardwalk. It was still like pebbles and dirt and a bit of scrambling. But now they've like literally made it like a proper boardwalk with railings, and it's, you know, your grandma can do it. And when you get to the very top of that boardwalk is an old weather station. And it tells you a little bit about the man that lived in this, like I'm talking, the cabinet is as big as one of these tables, if not two. And that's it, that's his, well, okay, maybe four. Let's be realistic, maybe four. And, you know, that's where his kitchen was, and his bed, and his one-room science study center. And he stayed up there all winter and all summer and recorded the climate of the temperature, how it increased and decreased throughout the year, of the levels of precipitation, how they increased and decreased. And then these go into data booklets where weathermen then get to hypothesize what next year might be based on the trends of the past, right? You've seen these in social studies, these data from years and years and years ago. He's one of these people that took this data. Okay, so Sulphur Mountain, you go to the hot springs. It's right there, same parking lot. So instead of going to the hot tub, there's actually a Starbucks there now, I think.
There is.
Yeah, right?
Yeah.
Starbucks? Yeah. So it's not that arduous. Okay, so in this weatherman station up at the top of this mountain he would have recorded it in millimeters of mercury, because he would have, you know, he needed an instrument and he would have had to make this instrument, and mercury was something that was nice for scientists to work with because it's a liquid, so it flows, but it's a metal. So it's still like, you know, it's still pretty solid-like for a liquid. That makes sense? So you fill this container with mercury and you put it upside down, kind of like a test tube with increments on it. Okay, so like little measurements. And you can imagine that this test tube, if this was a straw and this was your, you know, iced tea, you'd have liquid in your straw. Everybody okay with that? Okay, so here's some liquid in the straw and here's some mercury, right? Only it's not a straw, it's a tube. And if the pressure of the atmosphere increases, it pushes down on this pretty dense liquid. And if it pushes down, the pressure is going to exactly push up. And therefore the new level will tell you the new pressure. And literally, you're talking about millimeters of mercury up the tube. Okay, so that's where that measurement comes from, millimeters of mercury. Okay, so 1, 2, 3 different units of pressure. Okay, what is pressure? Do you know? Why does a balloon have pressure? Does a balloon have a pressure? How do you know balloons have pressure? Like here's a balloon, touch it. How do you know? I want to bring some balloons from home. Roll them up.
Well, like when they pop, they would make a sound.
Oh, okay. Why do they make a sound when they pop?
It's like.
Okay, so you've got some gas escaping really fast if they pop. Agreed?
Yeah.
So you know that it must want to go out if it can go out. Okay, I'll take that. So you know it has a pressure. Why doesn't the balloon kind of like, well, look like this? Like, does this tissue have pressure?
No.
Does that tissue have pressure?
No.
How do you know?
It doesn't.
There's no pressure there. Doesn't float? It's pretty easy to change. Can I feel the pressure?
Yeah.
How do you know when your pop bottle has lots of pressure that it's about to explode?
Oh, it's like super solid.
Super solid, right?
Yeah.
Super tough. And what if the pressure isn't and you can then squish it? So if you can squish something, it's like, you know, not necessarily the softness of the fabric, because it's the same fabric, right? So if you can't squish something on the pop bottle, there must be something squishing back at you. What is that thing that's pushing back at you if you can't push the pop bottle in?
Force or pressure.
The pressure of
Gas.
the gas particles. And what are they doing? Traveling in straight lines until they hit something. What are they hitting?
The bottom.
Uh-huh. So what's pushing against you? That gas particle, that gas particle, that gas particle, as they hit the sides of the container. So what is pressure? It's these gas particles hitting the sides of the container. There's another gas particle, there's another gas particle. And you know what this does? It keeps the balloon out. Because this is happening, you know, a gazillion times per second. So it keeps that shape of that container outwards. And then as soon as it hits it, it moves back in. Yeah, but another one then hits it. Okay, so what is pressure? Pressure is the force of particles hitting the sides of the container. Okay, so pressure is the force of particles hitting the sides of the container, pushing it out. So, and that's also why then gases expand if you let them, right? Because it's pushing. Okay, I can push further if I let it. I think there's one more thing on your sheet for me to talk about. It's STP and SATP. So if I am a scientist in Canada and I have a friend who's a scientist in Germany and we are designing an experiment. And I do my experiment on a balloon and I tell him my results. And he does the same experiment on a balloon, but his results are completely different. Like completely different. It could be because we used different pressures, temperatures, and volumes. Okay? So what the science community decided to do is to say, I'm going to do my experiment at exactly this pressure, this temperature, and this volume. You do your experiment at exactly this temperature, this pressure, and this volume. And then when we compare our results, we can actually compare apples to apples. Because you haven't used, like I've used a balloon, you used a brick. The results are going to be completely different, right? So for the same reason, your pressure, temperature, and your, whatever the last one I'm missing, volume needs to be the same. So, and concentration too. So they came up with this thing called, let's standardize our temperature and pressure, and let's call it standard temperature and pressure. So, or STP for short. So standard temperature and pressure says, well, every scientist has to do that experiment or get those results at 101.3 kilopascals. Okay, and a temperature of 0 degrees Celsius. That's pretty cold. Do you want to do your experiment in a fridge? Not really, right? So then they went, oh, okay, that's great, but it's not really realistic. Let's have also a standard ambient temperature and pressure. Ambient means room temperature or normal temperature and pressure, so that they can do it in a normal lab. So now they've upped the temperature to 25 degrees Celsius, and of course the pressure's changed to 100 kilopascals. Okay? So that's what STP and SATP mean, or they are certain temperatures and pressures that are regimented. Okay, so that's the introduction to this topic. You are going to do this graphing lab. You are pretending you are Boyles, and you've been given a lot of data about how the pressure and volume changed as you did your experiment. Okay, so he went and took a balloon, let's just say, he didn't really use a balloon, but, and squished the volume by a half and recorded the pressure. And he squished the volume by a third and recorded the pressure, and he squished, etc. And then that data is in this booklet, the data table for you. So the first thing it says is to very simply graph pressure and temperature. The second thing is, and the third thing is, the fourth thing is. So I'll help you work through this lab together, as if you were Boyles. And, oh yes, you're gonna hand this lab in to me, okay, as your first draft. And I will give you a homework mark for it. And then I'm going to make lots of annotations like, hey, your graph needs to be bigger, your line of best fit needs to look like this, etc., etc. So that the next lab you give me on the next thing in the package, I get to mark properly and give you a mark out of 10. And then you know how to get that 10 out of 10. Because that'll be kind of your rubric, this first draft. Does that make sense? Okay, so has everybody